Okay, so this is a complicated system. I hope you have your handheld model on hand. We are now going to talk about enantiomers, okay? And we want to say now, since enantiomers are different, they must have different names, right? Remember we said that a little bit ago. If you're naming something, you can tell if it's the same thing as something else if it's got the same name, right? Well, enantiomers are different. We've established that. They must have different names. The way we're going to name them differently is using a system called the Cahn Ingold Prelog system, CIP. The Cahn Ingold Prelog system has got a nice, unarbitrary way, systematic way to name things. If you practice it, you'll get good at it, all right? So we're going to call these things R and S, okay? And here's how we're going to do it. We are going to go to the four groups, and we're going to give them numbers. Now, in a previous conversation, I was using like square, circle, triangle, and hairball, right? So, but we're going to do better than that now, right? Because I was just doing it arbitrarily then. Now we're going to number them 1, 2, 3, and 4. And the way we're going to do that is we're going to number them according to atomic numbers. Yes, atomic numbers, all right? So then we're going to arrange the molecule in space. So first of all, we're going to prioritize them. Then we're going to arrange it in space such that the lowest group is facing away from us. You're either going to do that with a handheld model, or I'm going to make a couple recommendations on how you can do it with a pencil and paper. And then thirdly, we're going to count the group priorities 1, 2, and 3. If they go clockwise, it's going to be R. If they go counterclockwise, it's going to be S. All right, so let me demonstrate this. Let's go and demonstrate this, okay? So we come here. We say, hey, I got 4 different groups on here. Now, this must be a chiral center. So we're going to go with the highest. Chlorine has got a what, 19? I think it's 19, right? Oxygen is 8. Carbon is 6. And hydrogen is 1. So, yep, chlorine is number 1, and we got that. Chlorine's number 1. Oxygen's number 2. Yep, we got that. Oxygen's number 2. Aha, okay, so this is correct, all right? 1, 2, 3, and 4. Now, the atom with the largest atomic number, well, we already said that. We already said that. So we number them, all right? Now we're going to have to arrange it so that the smallest one, which is 4, has got to go in the back, all right? So watch this. We're going to rotate this in space. Now, if you have a handheld model, you ought to do it. Prove it to yourself. You honestly, you would be investing in your own expertise. If you would pause the video now and build this molecule. And then if you take this and you turn it around, you'll see that the oxygen is now, if you turn this around, you'll see that the oxygen, look at this. There's a hydrogen, right? There's a chlorine, right? This is the backwards of that, right? So I just did the mirror image of it, which we saw, I think in last video. You can just draw the mirror image, but rotated it around. And so now the hydrogen is in the back, right? You see that? There's my lowest group in the back. Here's my number 1 group. Here's my number 2 group, and here's my number 3 group. Okay, so let's look at the next slide. You see that? My number 1 group was there. 1, 2, 3. Let me go back a slide. See that? Same thing. 1, 2, 3. This is counterclockwise, right? Did you see that? So that's an S. All right, you see that? Counterclockwise makes that an S. All right, this is a nicer picture of what I had on the previous slide. All right, so it's counterclockwise, that makes it S. Let's come back over here now. Let me go back. Where are we here? Okay. All right, so now if you've got groups that are where you've got a tie. So look at this. I've got a carbon atomic number 6, and I got a carbon here, so it's a tie. Do you see that? This is my number 1 group, though. Oxygen's the biggest, and hydrogen is definitely the lowest. But if I have a tie, I got to go out to the next group. So now that we've got that, we go out one more. This one's got 2 hydrogens on it. CHH. I'm sorry. No. This one's got a hydrogen on it, a hydrogen and a carbon. That's where that CHH comes from. Let me say that over again, okay? Watch this. Okay? I go to this atom here. It's a carbon. So we got to go out one more. Well, this carbon's got 2 hydrogens and another carbon on it, right? This carbon has got 2 hydrogens. Oh, I did that. Man, I'm really sorry. That's already here, right? A carbon and 2 hydrogens. Now we go out to the next one. This one has got 2 hydrogens on it. Sorry about that. And this carbon has got 1 hydrogen and 2 carbons, right? 2 carbons and a hydrogen. 1 hydrogen and 1 carbon and 2 hydrogens. So this one wins. Wow. That's complicated. I hope you got that. So this, let me go to a different color. This is number 1. This is number 2, right? This is number 3, and this is number 4. Okay? Now, sometimes if I'm confused at this point, which is, as you can see, not altogether unrealistic, I might redraw it. Say, all right, watch this. 3, 2, 4, and 1. See, I'm very patient. Well, I'm going to just take my time and just redraw it. Now I can look past all those notes, and I can just look at this. Okay? And I can see, by the way, that the 4 is not in the back. All right? So, now that we've got that, you know what? Sorry, I want to go back and do this. Now that we've got that, can you see what I'm going to do here? I'm going to say, all right, well, since my 1 and my 4 are not in the back, I'm going to do a little twist here. Twist it in space. My 3 is over here. My 2 is over here. Do you see what I did? Actually, I really turned it that way, right? Really turned it that way. And my 4 is over here because I wanted to get the 4 and back, right? Now that I've got the 4 and back, I do my arrow from 1, 2, 3, 1, 2, 3. This is clockwise, and so therefore it's R. Wow. Oh, I love it. Okay, so let's do another one. We have another tie here. In this case, yeah, oxygen's 1 and hydrogen's 4 because we're dealing with carbons here, right? Let me go back to red. Dealing with carbons. So this carbon has got 3 carbons to it. You see that? Carbon, carbon, and carbon. This carbon's got 2 hydrogens and an oxygen. Okay? So can you see that's the tiebreaker right there? The oxygen to the carbon. So this is actually going to be, even though it's the overall group is less massive, because 3 carbons weighs more than an oxygen and 2 hydrogens, still we take the highest one. This is just like playing Risk. When you use dice, right? You always take the person's highest die and compare the 2 highest die. All right? I don't know if you ever played that game before. It's so fun. All right. So having said that, now this then is number 2. This is 3. This is 1. And this is 4. And I'm going to say, I'm going to redraw it. 4, 1, 3, and 2. But my 4 is not in back, so I got to turn it this way to put 4 in back. That'll bring 1 to the front. 4. It's going to bring 2 over here and 3 over here. 1, 2, 3. R. Okay? So let's look at one more kind of tie here. In this case, or one more question about the Cahn Ingold. It's not really a tie, I don't think. So let's look here. We've got a carbon here with 4 separate things on it, right? There's an ethyl group. There's a butyl group. There's an acyl group. And there's a methyl group, right? So this carbon's definitely chiral. But look at this. When we go out here, that carbon has got 2 oxygen bonds. And so we write it out as 2 oxygen bonds. That's what that's about. The oxygen atom counts twice because there are 2 bonds to it. All right. Now, here's some other tricks. If you want to get number 4 and back, so we showed the one trick, right? The one trick was just turning the whole thing around. But another trick is to only switch 2 atoms, any 2 atoms, and just assume if you started with S, your new model is R. So does that make sense? any two switches is going to switch from S to, I'm sorry, any two atoms switched or any two groups switched is going to change the orientation. All right, so in this case, if you want to keep the orientation the same, you just make two switches, right? So the first thing I do is I put the lowest group in back and I switch it with the 3. So it puts the 4 in back. Do you see that? And then I just make another switch, any switch, it doesn't matter. And because any two switches, any switch of two atoms is going to reverse the configuration. So I switch it once, and again, if this was an S, it goes to an R, and then one more switch takes it back to an S. If it was an R, then one switch is going to make it an S, and it's going to go back to R if I make a second switch, right? So switching two of the groups twice returns the original configuration, but it allows us to put 4 in the pointing away position. All right, so here's a table for the review, the Cahn Ingold Prelog rule. Identify the 4 atoms, assign a priority. If 2 atoms have the same atomic number, figure out how to break the tie. Rotate the molecule so the 4th priority is in the back, and then go 1, 2, 3, 1, 2, 3, R, or 1, 2, 3, counterclockwise, S. All right. So now that we've got that, we've got R2 butanol. We notice that the R is going to go with the, there's only one chiral center here. I'm going to show you this one, even though I know this video is taking a long time, but I think it's worth it. Okay, so let's go here. We've got a hydrogen here. That's convenient. Hydrogen's already in the back. So oxygen's my biggest one, or my highest priority. 1, 4. So one of these is 2. I can see this has got 3 hydrogens on it. This only has 2 hydrogens and another carbon. So this is going to be number 2. And this is going to be 3. 1, 2, 3. Clockwise, R. Okay? And obviously, if I switch it, it's going to be S. All right? Here's one with 2 chiral centers. And if you have 2 chiral centers, you don't just put the R or the S out front. You say at the 2 position, it's R. And at the 3 position, it's S. Right? This is going to take lots of notes in order to do something like this. Get good at it. You'll never get it wrong. It'll be free points on the test. All right, now it's important to appreciate that because the structures of enantiomers only differ in the way that, with respect to the mirror, they only differ like your right hand does to the left. They have the same physical properties. Yes, the same physical properties. However, like look at boiling points, melting points, same, right? They in space, if you were to take the mirror image of it, it would look identical. However, they do affect how they interact with chiral compounds. So if you have an enzyme in your body that can only deal with this shape here, then it will not deal with that shape, right? So they only interact they only affect how they interact with chiral compounds and their optical activity. Optical activity, and that sounds like a good subject for another conversation.